Hello. Yeah. So my talk will focus on JavaScript and why and our recent efforts on static analysis of JavaScript. So before we start, I'd just like to give a quick overview of how JavaScript works. So like any other managed system, like a virtual machine, we have source code that goes into the system. Then we have a parser, an AST. Some implementations like to interpret the AST. Over time, when things get popular, they get converted to bytecode. Eventually, this bytecode gets compiled to native code. So this is the traditional pipeline, and there is really not much different between these languages. The real distinguishing part of why we really think static analysis of JavaScript might be useful is in the language extensions and frameworks and libraries that are built on top of it. So let's take one case study. Let's look at React. So React is extremely popular. It's a way to describe user interfaces. And it has some language extensions to JavaScript which make the life easier. So in order to understand this, let's look at what a user interface is. So you have a user interface that's a picture, and when you touch somewhere on this picture, something happens, and then the state changes. So one beautiful way that this gets modeled in this system is it's looked as at a pure function. So y is a function of x. The picture that gets drawn is a function of some state. And this state in a React sort of a system looks like this. So we have an array code added, and then you have items. So if you think about the brain map of how this sort of a program will look, the most natural representation that gets used is you break down your program into these components that are responsible for drawing different parts, and the input to this program is a state. And when you give this state as the input, corresponding output is drawn. And the key idea behind these sort of descriptions is there is a way to handle computations in state. Whenever we, let's say, press this add button, we have a recompute state that happens and which modifies the state. You add something to the state and then this computation happens. So we have this sort of a mental map of how the program works, and in reality, this is also how the program looks. And if we destructure this program, take out the high level syntax, start breaking it down. So you take the high level syntax, break it down into its components. We find that we end up losing all that nice high level information that existed at one point, and now we are just left with functions. So one of the reasons that we believe like why JavaScript even became famous is it has really useful abstractions. A lot of people will write servers, but Node.js servers just simply run really well because the model of threading is so beautifully implemented that it's a cooperative threading model, but where you cooperate is decided by the framework. And it has frameworks that help you describe functional user interfaces. And then it also allows you to maintain code bases so you can write your applications that work across different systems. And, and and when we come to the compiler part of it, we have more than like I think 12 or 13 popular implementations of the VM itself. And this is because there are really good documented test cases, working groups, and the way the language proceeds as a whole. Just to give you an example, the latest Babel transpiler takes the latest JavaScript specification and tests it against a virtual machine that dates back to 2015. So they have really good backwards compatibility and very well maintained specification as well. And with all this comes wide adoption. So this was one of the reasons JavaScript is so popular and why it matters today. And as a compiler developer, what we would really like to do is perform some traditional static analysis. And to this end, we want to take the language specification that exists, convert it down to a slightly simpler representation. And once we have this basic framework built, we'll be able to hopefully do more analysis on top of it. So let's look at one simple example. We have this piece of code on left. So we have a bunch of expressions, and then we collect the result here and we log this value. And what a straightforward transformation might look is just take all these three, put them in temporaries, and this looks straightforward. But the catch here is it's semantically incorrect. So it's not semantics preserving. So even though JavaScript supports anonymous functions, functions are first class, the semantics of JavaScript themselves are complicated, and because of these complicated semantics, even simple transformations that you make to the program will end up rendering the program wrong. So further analysis will be wrong. And, and on top of this, the syntax itself has support for strange syntax. So we see we are building a class here, and what the first thing means is not even clear in this case. So if we just go over the program one by one, what we realize is when the function gets called the first time, it's not even really a function. It behaves like a new thread creation. So even though functions look like functions, they might end up creating first class continuations. And so the details of exactly how this happens are maybe people who are not completely familiar with JavaScript might appreciate. But the point is, functions look like functions, but they don't really behave like functions. And functions are really not even functions; they are objects at runtime that can have properties. So this is the scenario of JavaScript, and why translating or transforming the code might be not so straightforward as one would imagine. So, in our recent efforts, what we are trying to do is take the complete JavaScript specification and convert it down to a smaller specification called 3JS. And along the way, we came across these different problems that are interesting enough that we thought we'd discuss about them. So, one of the simplest transformations that we had when converting the code was of this form: o dot f equals 10, and this is not semantically equal to the second statement. So even member expression lookups in JavaScript can have side effects. Apart from these, there are really complicated semantics. So what we found when we were building 3JS was, okay, so the text is not intended to be read because it's not very clear. So what we found was the same source code parses differently if you pass in a different mode of operation. So JavaScript, apart from being a really complicated syntax and semantics, has different modes of operations where the same source code will parse differently, and if one identifier is a keyword in one mode, it might not be in another. And sometimes even things silently break. So if we were to transform this piece of code, so we have a function call here which we want to break down, this ends up breaking the semantics. The program will run, it will not throw any syntax error. We have not broken any syntax rules at this point. But even though we did this and it looks right and it runs, it gives us the wrong answer. So some semantics of JavaScripts are described at runtime. So if we want to do a correct transformation, we need to take all these things into account. And apart from that, we even have some strange syntax. So over the years, over last 10, 12 years, JavaScript specification has extended and extended and extended to support the requirements of a lot of people. And one of the things we found was you're allowed to write things like these, and these are completely valid in JavaScript. So you can have delete of z, z is an integer, and if you do a traditional three address code sort of translation to this, you generate the AST, store intermediates, and generate the following piece of code. This gives us the wrong result now, and a lot of and the reason we have access to a lot of these test cases is JavaScript provides an extensive test case suite of like 40,000 plus tests, and that's where we found all these interesting semantic rules that JavaScript has to offer. So when we dug deeper into why this semantics is the way it is, what we found was the delete operator is whenever it sees an R value expression, it simply returns a true. So when we did this translation to 3 address code, we changed this R value to an L value, and because of which we got a false. And on top of this, when you dig deeper into the specification, what it said was, even though this is supported in our language, it is not really meant to be used. So what it exactly says is the syntax allows a wider range of expressions following the delete operator, but only the following forms lead to meaningful behaviors. So the full JavaScript language has support for a lot of these possible behaviors, but not all of them are really meaningful. So our main goal was to subset the language in a way most people use and then perform analysis on top of that. So to this end, our current work in progress, we call it Iridium. So what we are trying to do is convert JavaScript to a slightly more manageable subset of the language. So we would like to have some basic utilities needed for analysis, which we are currently developing. And we would like to model high-level features. So when we take this JavaScript code that has first-class continuations that get generated, and then you have language extensions, we would like to keep all this high-level information around until the end, so we can optimize and do more sort of analysis. So this is what our pipeline looks like currently. So we taken different kinds of projects. We so we take in different kinds of projects. We identify the different modes of operations in which each file may run. We then parse them using Babel. So Babel is a popular standard JavaScript parser. And then we have different parsers to resolve imports and generate module graphs. So one interesting aspect of JavaScript is, even when you're running a file, you cannot know what all code it runs, because what all code it runs can change dynamically at runtime. So you're allowed to import or resolve imports at runtime. So some of the pre-analysis that we do is just figure out all the static imports that can happen. And for the dynamic imports, we would like to analyze them in the future. And then we have a JavaScript 3 JS3 builder. So it builds a specification, there's a smaller subset of JavaScript called 3JS. And, and then we have a few other utilities that we are building around Iridium that make it easier to analyze JavaScript. And in order to do a iterative subset of JavaScript, the way we went about doing this is create a stub generator called JS3gen. Uh, and what this does is takes as input a language specification, which in this case is the JavaScript specification. And then we have a restriction file that's described in a JSON. And it generates code in order to handle all the relevant methods to generate that subset itself. So this was our approach to do. So to do this, we taken the type specification of both the original and reduced language subset, and then we generate the relevant subsetted type specification and the constructors. So, so the main reason is we are putting in all this effort, and what even is the rationale behind analyzing JavaScript as a language. So if we think about modeling high-level concepts, so if we take, let's say, closures that we can define in C++ now, and if we look at the standard function and which just returns 11, so we see that it captures no environment, so that field is empty, which denotes that nothing is getting captured. So this is essentially just a constant function. But and when you analyze this code just by looking at it, it's easy to see that result is just number 11, because that's essentially what it's doing. You call foo. Foo creates this closure which just returns constant 11, and then you return this constant function. But when you but this is not exactly what it gets optimized. So when you run it through Clang, this results in 3,600 lines of code with 148 functions and so on. So the hypothesis here is, if you model these high-level concepts like closures, continuations that get created at runtime, we'll be able to optimize, we'll be able to push optimizations that depend on these high level language features, which can propagate downwards. So one of the previous works that we did was to optimize functions in R, and we realized that when it gets converted to LLVM, it's really difficult to distinguish promises, lazy code, and regular code. So you can't optimize it after it loses a level of abstraction. So in conclusion, JavaScript may very well be impossible to analyze statically, that there is a good reason people don't do it. But but there are millions of lines of JavaScript code that are totally pure. You have out of the top 10 applications that are on the App Store or Play Store, a lot of them are written in React. And React apps, maybe even Electron uses a lot of React based UI design. And we believe that all this code is just totally pure, because we discussed a mental model of how user interfaces are described, and keeping around this high level information can help us optimize code. Like we can have them execute in parallel because these functions have no side effects. We can even delay their computation, create them into thunks. So this is the motivation we are working towards. And our previous experience with R is also sort of supports this conclusion that if you keep around high level information, you might be able to optimize the code even more. Thank you.
Excellent presentation. I wanted to ask about a few things and point one thing. How are you thinking about parallelizing JavaScript? Because Node.js as a runtime executes as a single thread most of the time, other than workers threads. So how are you thinking about doing that? And also just to point out, many of the people here are C++ experts, but SED function is just a type erase function, so obviously it won't get optimized with Clang or GCC. So, anyways, first, how are you willing to optimize and parallelize JavaScript code?
So, so Node.js proposes something that is that allows people to write massively parallel code. So even though it says blankly in its first line that it's a single-threaded environment, it's actually not. It is a cooperative threading environment where the cooperation is decided by the framework for you. And the places where cooperation happens is the places where code is probably going to wait. It is IO operations. So this thread pool, the way it functions is whenever you reach one of these IO statements, you just stop and push the continuation to your thread pool, and then you pick up another thread which is ready to execute. And the reason it is single threaded and doesn't run into these data races sort of problems is you don't stop at any other point. You only stop at places which are designed, which it is designed to stop at. So this is the problem here. So even though this works great, you can write code that handles like 50,000 clients easily. But the problem here is you can actually benefit more if you convert this apparent parallelism to real parallelism. If there are two threads that wait on different resources and execute on different memory locations, then they have really no reason to wait in this pool. They can actually run in parallel. There is no such dependence. So if we are able to analyze code at a high level to discern this fact, we might be able to convert this apparent parallelism to real parallelism. That is our hope. So that's what we are trying to do.
Okay, so just to confirm, you are talking about JavaScript executes as a concurrent system. So async awaits are basically a concurrent single-threaded mode of doing things. So you are trying to parallelize it for actual like OS threads, right? OS threads and Node.js threads.
Yes.
Okay.